Alrighty, so in this video, I'm gonna go ahead and derive what I call and what some other people that taught me this stuff have called the FIFE equation. You'll see why it's called that when we get there. But basically, this is the equation that we use to solve RC circuits. Okay, specifically simple RC circuits like the ones that we're gonna cover in this class. And I'm gonna try and get through it all in one video. If it gets a little bit long, then I'll stop it and break it up. But I think I'm probably just gonna try and plow through it in one video so that we have that. So it's just gonna start out with an RC circuit. And of course, I'll label my voltage source VS. I'll call my resistor R, and I'll call my capacitor C. And then I'll label my node voltages. I'll call this node VS, and I'll call this node VC. And of course, my voltage VC is just the voltage across the capacitor. Okay, and then I'll label some currents here. So I've got a current that I'm going to label flowing down through my capacitor. That's IC, which we know is just C dVc dt, right? That's the equation for capacitor current. And then I'm going to label this other current here. I'll just call it I1, okay? You know what, for the time being, I'm just going to call this one I2 just to stay consistent. But we know that that's the current through the capacitor. And so if I treat this as my node and I know KCL, then I can say that, you know, the sum of the currents leaving the node, the sum of all the currents leaving the node are equal to 0. So I could say I1 plus I2 is equal to 0, right? So I1 leaves the node to the left and I2 leaves the node downward through the capacitor. Well, I know my expression for I2, that's just C times dVc dt. And I can pretty easily get my expression for I1 using Ohm's law, right? The voltage drop across my resistor here is going to be Vc minus Vs, right? Vc minus Vs, and then that whole thing divided by R. So I can add those two terms and set that equal to 0, and now I have this expression that I've derived from KVL. All right? And so with this expression, I can go ahead and solve for Vc in my expression. It's a differential equation. You may or may not have learned differential equations already, but I'm just going to go through the math just to show you this expression, because like I said in the previous video, what we're interested in is if this is my Vc of t, I'm going to be interested in plotting that as a function of time, right? That's what I'm interested in finding here. And so if I get Vc of t, then I can also get I of t as well, because I know that the current is just the derivative multiplied by this capacitance, right? So if I get the expression for Vc of t, then I can easily find the current expression as well. So that's the point of this this exercise, is to get an equation that we can use to determine the voltage across the capacitor in these circuits. Okay, so let me go ahead and just keep going. What I'm going to do is I'm going to actually separate this into two sides here. So let's just say Vc minus Vs over R is equal to negative C dVc dt. All right, and then I can actually take the C over to the other side if I divide both sides by negative C. So what I would end up with would be Vc minus Vs divided by a negative Rc, and that's going to be dVc dt, okay? So from here, let me actually just drag this over here, and I'll continue the math over here so I don't run out of room. And what I'm going to do next is I'm going to multiply both sides by dt. So this cancels, and I'm left with Vc minus Vs over negative Rc times dt is equal to dVc. And so the very last thing that I can do here is I can move this voltage difference term over to the other side. So I can say negative 1 over Rc dt is equal to 1 over Vc minus Vs dVc. All right, and now what this is called is a separable differential equation. Well, we already had a separable differential equation. up above, but now it's ready to be solved. And so what you can do now that the variables are separated, right? I have all the VCs over on this side and I have all the T's on the other side. I can integrate both sides and I can solve for VC. Okay, that's the goal here. And so let me go ahead and do that. All right, so in this left-hand side, I'm going to integrate over with respect to time. I'll start at time 0 because that's typically what we're dealing with in an RC circuit, is that we're going to turn this voltage source on at time t equals 0. Let me actually draw it like that, more of a pulse rather than a DC source. So I'm going to go from 0 to some time t, negative 1 over RC dt, and I'm going to set that equal to the integral on the other side. I'm integrating from, let's just say, I'm going to start at some initial capacitor voltage, VCI, and I want to integrate out to some capacitor voltage at time t, okay? And I'm integrating 1 over VC minus VS with respect to VC, okay? So on this left-hand side, this is pretty easy. This just comes out to negative T over RC. Not going to go through that. That's pretty self-explanatory. And then if I take the integral of this right-hand side, it's a little more tricky. It's actually going to come out to be a natural log of VC minus VS. And I have to evaluate from my initial capacitor voltage to my capacitor voltage at time t. So let me write that out. That's going to come out to the natural log of VC of t minus VS minus the natural log of VCI minus VS. And then that can be rewritten, if I use my log rules, as the natural log of VC of t minus VS divided by VCI minus VS. Okay? And so now what I can do is I can exponentiate both sides to get rid of my natural log. So I get this e to the minus t over RC on the left, and on the right-hand side, I can drop my absolute values now that the natural log is gone. And so what I'm left with is just this term here. I can multiply this piece over to the left, so I'll do that now. I'll say VCI minus VS is multiplied by e to the minus t over RC. And I can say that that's equal to VC of t minus VS. And now all I need to do is add VS to the other side. So let me just go ahead and do that. And now I have an expression for VC of t, okay? And this is the FIFE equation. And why the heck is it called that? Well, if you look at the circuit that we started with, typical RC circuits, whatever this source voltage is, so say I pulse this source from 0 to 5 volts. At the end of some time t, after a long time after we pulse this source, this voltage here is going to be the voltage that I have across my capacitor. That's my final capacitor voltage. Okay, so I can, instead of saying VS, I can come in here and change these VS's to VC final, the final capacitor voltage, okay? And so, or better yet, I could even just do this right here, and I can say I want to evaluate as VS is equal to VC final, okay? And now this expression, let me pull out my highlighter here. I have VC final plus VC initial minus VC final multiplied by this exponent gives me VC of t. And so the final, initial, final, and E give us an acronym that we can use to help us understand, or not understand, but memorize this equation, because this equation is vital for using, for solving RC circuits, okay? It's vital for solving charging RC circuits, or it's vital for solving discharging RC circuits, and it's also useful for solving RL circuits as well. So it's pretty important to memorize this equation. You can always derive it yourself, but it's very important that you understand this, and the FIFE acronym really just gives you the picture of what the expression looks like. It's going to be final, initial, final, and E. Okay, and then in the next video, I'll go ahead and talk a little bit more about the equation and what it means. But for now, I just wanted to go through this derivation. I know this video is probably a little long, really math heavy. Don't worry about the math. I just like to derive things and show you where they come from. Your job is going to be to utilize this equation to solve RC circuits and to derive the expression for capacitor voltage, current, and when we get to RL circuits, we're going to use it as well. Okay, so I'm going to stop this video right here.